in the last section, we finished off with motors. We've done dynamos, generators, we've done motors. Remember, right hand, left hand rules, left hand motor, right hand dynamo. And you're always going to have to just find one of the others, all right? And as long as you know how they fit together, the drawings and the mechanics of it, it's really quite a good section to earn good marks on. A lot of it is draw it, and if you know how to draw it and label them, you're A for away. Now, the next thing is we're going to look at this piece now. We're going to look at alternating current, all right? And it's in some syllabuses and some it's not. But we're going to deal with it anyway for completeness sake. Now, alternating current, right? What is alternating current? Fundamentally, alternating current is that one where we said it comes, okay, out, and it's doing that, okay? So my voltage, let's say, is there, or shall we just say that's current? Forgive me, this is current. And I'm going to put voltage in blue, all right? So my voltage is going to be over here, possibly, all right, like something like that. So this is a V max, and at the bottom, we've got an I max. You can see that the current, okay, is essential. I've made it less than the voltage just to get a delineator. Now, the current is a maximum. The voltage must be a maximum, right? Now, what are we saying? We're saying that this is alternating current, isn't it? But what does a battery look like? Okay. That's alternating current. What does a battery look like? A graph of a battery's power, a current and voltage. Okay. Voltage stays at 12 volts, for argument's sake. Current stays at 2 amps. All right? Or let's make it a little more realistic, 0.25 amps. All right? So there's a difference. This here is a battery. They are constant. Spot the difference here, shall we? Hang on. That's variable. These are variable. Right. So now we have a little dilemma. How do we define power in a battery is V times I? How do we find this is in a battery? How do I define it for alternating current? What do I do for alternating current? Alternating current, I have a problem because in the name it alternates. What do I use for V and for I? How do I get the power that comes out of my plug? Many countries are AC, some are DC out of a plug. It doesn't matter. When it comes out your plug, it's going to have a shape like that. Even if it is DC, it's going to come through in a waveform. It doesn't come out in a nice smooth line. So what do we do? Well, we have now got, let me just take, for example, okay, let me just take a graph like this just to illustrate it, shall I? Okay. Now we want to be able to somehow, okay, work out the power. Let us just say that there is going to be, let's call it I. That is I max, correct? Now, what do we do? Well, what we do is we find an average. So we say, all right, I'll tell you what we'll do. Let's just split you up like that. And then we'll say, all right, we'll draw a line through there. So that that area falls in there. That area goes in that piece. That area goes in that piece. And you can see all I've done here is I'm doing some kind of average. All right? I'm finding out where essentially I can draw a straight line so that the top bit fits into the holes in the bottom bit. I'm equilibrating areas, really. That's what I'm doing, aren't I? So I say, okay, now by doing that, I have introduced a term. And I'm going to call that term RMS. and it's known as root mean square. All right? And basically what we're saying is that P power is equal to V max over root 2 multiplied by I max over root 2, which is equal to V RMS multiplied by I RMS. This is the root mean square. And I should always learn my lesson not to fiddle once I have put a number down. Right? That is VRMS. So VRMS is equal to V max over root 2. IRMS is equal to I max over root 2. Straightforward. Okay. This section's actually, as I say, it's not often asked. All right. So effectively, we're saying that these are the effective I and V. All right. That's what I'm going to be using in my calculations for power and things like that. I can't use the maximum. Okay. And no. Well, why can't I do this? Okay. Why can't I do this? Ooh, not draw a line there. That. Okay. Why can't I do this? Why can't I just say, well, it's going to be half of V max? Well, if it was half of V max, that would work. If I had something like this, right? I could say, well, take it and that will go into there. It's linear. But it's not half. Can you see that? It's actually 1 over root 2 is 0.707. Okay? So what we're saying here is that, okay, well, that's at 0 and 90 degrees. 0.707, if you go arc sine of 0.707, shift sine 0.707 is equal to 45 degrees. Okay? So what we're saying is, yeah, that's kind of moving towards a sine curve now, isn't it? But yes, just forget that little bit. That's not really the issue here. The issue is that I can't say it's half because I'm building up. It's not a straight line. Okay? It's not triangles that are in there. You can't use a midpoint formula to solve this because it's bent up. So I have to find a line a little bit higher. So essentially, what we have is we end up by saying that my effective, so my V RMS or my I RMS are going to be the equivalent battery, I or V, right? The RMS is going to be, in other words, it's the long average of the two. Simple. Now, all right, let's just move along a little bit with this. All right. That's essentially how we're going to do power, etc. But now, you know as well as I do that these things, when we charge phones, okay, when we are running appliances, all right, very often things don't always work at 120 or 220, 240 volts, okay? They don't. They run at a different voltage, usually lower in the house, right? You've seen these overhead lines. They are very high voltage lines. But how do we get that voltage down to our house and into our appliances to run them, okay? Because not everything runs on 240 volts. Well, we then have to use that good old thing called a transformer, okay? So now we're going to look at transformers. All right? A transformer, basically what it's going to do is it's going to take a voltage that we have. So it's going to take, I'm just going to draw here, V input, a voltage input, and it's going to give us a V output. All right? And the V output, if we put in 240 volts there, I want to say 12 volts comes out there. Right. How do we do that? Well, first of all, let's go back and consider. Remember, let's first look at the input side. What is happening here? Remember, there's an input here of 240 volts. It's AC. So it means that this is plus minus and then minus plus. So here we've got a coil, right? So the current runs up there and then down, and then up and then down. So what happens? Initially, I have a north and a south there. But then again, it changes to a south and a north because the current reverses. So what is going to happen? Now, let's just stop it at that point. Let's say we've got now inside this we've put, it's a metal core. Why? Because it makes our magnet stronger, doesn't it? Magnetic field stronger. So what is this? This is like a fountain. Coming out of here in all directions are north. Let's just say we stop time at north. North is there. So we've got our flux lines. Let me draw a flux line coming out. Okay? Let's take a flux line on the black one. So north is going to come out the top here because inside there, all right, okay, I just want to draw it a little over. So over here, this line comes all the way, all right? This is my north and it's coming in like that, isn't it? So these are cascading out. Forget what's at the output side at the moment. So I've got this fountain cascading north. So I've got magnetic flux line running this way, right? Now what happens is it changes to green. Okay? So when it changes to green, what happens to my flux line? All right? It does that, doesn't it? It changes direction. So I have got a changing magnetic flux over here. Let's just consider what's happening here now. Okay? Because I've got this coil here, I've got north-south line. Suddenly it becomes north-south and it changes. And then back and then changes. So inside here I have got a changing magnetic flux field, right? Well, what happens now? We've got on the other side, on the output side, we've got some coils. Okay, maybe less coils. So inside here, there's a magnet's field going in, out, in, out, in, out. Hang on. What happens in this coil if there's a magnetic field? What's happening? In, out, in. Remember? In, out, in. So what's going to happen? It's going to generate a current, an EMF. So yes, because of this alternating magnetic field, okay, coming through here, I am going to end up with a alternating current here. I've got alternating in here, AC, AC out. So AC in, AC out. Right? It's all because this side had a north that way and then a south. And then a north and then the magnetic fields. So I put a coil here. Magnetic fields going through coil means I generate a EMF and a current through that one. Therefore, in a magnet, what do? I fill it so that I have, and these are in your books, and as I've said, I'm not an artist, please. So, okay, I've got something that looks like this, and a chamber that looks like that, all right? And on this side, I have windings here, all right? Boom, 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 okay, there. And this side we call the primary. This is my AC input. Okay, this is called the AC output, and it is the secondary. So if I've only got 3 coils there, all right, like that, then I say NP is equal to number of turns on a primary. And I've got NS is equal to number of turns on a secondary. All right? And then there's a formula that comes out of it, and the formula is NP over NS is equal to VP over VS. Okay? Now you've heard of the term step up and step down. Okay? If I've got over here, okay, this is my primary. What if I put more coils here? Okay? This is my V out. V in is less than V out. I got more coils. Remember, EMF is equal to minus N. That's where it comes from. Changing magnetic flux over time. Okay. Now the changing the time, okay, in this case is going to be the frequency of this usually is equal to 50 hertz. All right. Therefore, the time period in which it changes is 1 over 50, right? Is 0.02 seconds. So it changes, the current changes direction in 0.02. Okay? It's fast. Okay? What we've got then is this is called a step up transformer. This is a step up transformer. Step up transformer takes an input voltage and makes it bigger. You usually use those on a transmission line. When you have here, we have our generators, okay, whatever they are. And then we go through here and we have what's called a step up. That takes it up, and you've got here, you've got your power lines. They're normally called HT transmission, high tension transmission lines. Okay? Or various other bits and pieces. Now we come down to the suburb and we go and we do a step down. And we might even have 1 or 2 different steps downs before we get to the house. The step down takes the input voltage and makes it less. You don't want 380 volts in your house, right? You want something you can work with. And preferably you want to keep it away from being lethal. All electricity is potentially lethal. But yeah, if you put 1200, you're probably going to fry everybody. So you put it in at a voltage that we can work with. So that's the step up and the step down transformer. All right. What they also just talk about in this is conservation of power. Conservation of power. All right. What they actually mean is that power input must be equal to power output, which means V primary times I primary must be equal to V secondary times I secondary. Remember, power in, VP, IP. Remember, you've got to use your RMS, depending upon what you've been given, okay? We're using here RMS. Must be equal to voltage secondary, I secondary. Okay, conservation of power. Not totally true, because you know, if you touch your transformer, it's hot, right? So what happens is we're actually losing heat as it goes, right? So the energy isn't necessarily totally whatever, it's changed into heat as well. Now, and transformers are usually, just made a note here, they are usually 50% to 60% efficient. What is efficiency? Okay, that's actually very low. It means actually that you only get 50% out of what you put in. So your output is half of what you put in. So therefore, 50% of power in is lost, in inverted commas, to heat. Okay? There are eddy losses and things like that inside the transformer. So what we're doing here is we say that's just a guide for those of you who wanted to know a bit more about it. All right, now the last part of this piece is, but you know as well as I do that things that specifically operate on batteries, like calculators, they need a constant voltage. They need a plus to always be a plus. Otherwise, the chip's not going to work. So how do we change AC to DC? So we're now going to look at AC to DC. And the process used is rectification. Rectification. All right? So what we're going to do is we want to put in a signal or an input wave like this, which is a plus and a minus. This is our AC. And what do we want out? Well, we want out DC. Now there's two ways that we can go about this. Okay? The first way is we say, right, let us just have a circuit that looks like this. Okay? And here is a V input, and it is AC, usually denoted with like a little wave like this. Oh, Kevin. Like that, okay? AC. So it means this is plus and minus, and then it's going to switch to minus and plus. We put a little piece of technology in there that is called that, okay? And I'll get back to that now. And then we have on this side, we have an output. Okay, so we connect up another circuit to this. Whoops, not circuit spelled like that. Another circuit here. Okay, our cell phone charger, whatever it is. Okay, what do we have? This thing here is called an L. Okay, it's called an LED. LED. Light emitting diode. What it means that the current can only flow that way. Current cannot come that way. It can only flow in the direction of the arrow. So now, how do we do these problems? You start off with a plus and a minus and follow the plus, the currents going through, which means this is plus and that is minus, correct? Okay, happy with that. Now, when it changes to green, green is this way, hold on, the current can't flow. So when it's green, there's no current flowing because it can't go back that way. This electron that was shoved through, it can't go back, right? So essentially all I've got is I've got a plus and a minus, and this side I've got nothing when it's green. So what does the waveform look like that comes out of that? Well, let's plot it. All right? It's quite straightforward. Okay? What have we done is we've got this guy and nothing. So where this used to be for the AC, this is going to be the green piece. Can you see? It's gone. So we end up with a waveform looking actually like that. All right? That is half wave rectification. Okay? It's half wave rectification. All right? And basically what you've got here is you've taken out the negative. It can't go that direction. Well, that's not good enough because it means that our current or our voltage, our EMF or our current, whatever, it's going to be a break in it. We don't want that because it's going to go dead. So we say, all right then, let's see if there's another way. Now I'm going to draw a thingy here, which is in most books. So here's our V input and it's AC. So it's a plus and a minus, and I'm going to change it right now, minus and a plus. Okay, now I'm going to put the circuit in. We go up, all right, then we come down this way, and over here, I've got a light emitting diode over there, All right, I've got another one going down over here, like so. All right, like that. Then I've got another one going up there, arrow like so. And on this one, just take a little bit out of that guy. And over here, I've got one going in this direction here. All right, that now goes to a terminal, and this guy comes in, all right, connects up to this side here, and then this wire comes out to there. This is now my V output. All right. Now, what did I say? We follow the current. So plus first. So we go I goes this way, I goes this way, which means I can go through here, I, and my I becomes plus over there, right? So my plus is there, and it means that my minus is on the other side. All I do is I followed the plus. The electrons are flowing that way, plus, plus. So everything connected to plus, while it's staying plus, before it switches, is a plus. And you can see the current can't go down that way. So it means that's a positive, so the other side must be a negative. Then what do we do next? Next we follow the green one. We say, okay, it's now here. All right? So we've got I comes this way now, doesn't it? Okay? Because it's plus. We go along, I goes through here, and it stays plus. Okay? And what happens then is the minus will stay a minus. So basically, it stays plus, plus, and minus, minus. So as the wave comes in on the input side, okay, let's just have a look. As the wave comes in on the input side, like this, all right, this is plus and that is minus. What happens on the red? I think it was red that I used. Just let me just check. It was. So when it's red, all right, that was the plus side. So the wave built up. So that was my terminal stayed plus. This one was flipped up. It went to there and it became plus. So my output, the black was my input, and the red is my output. Right? It went that way. Technically, this is the green bit, isn't it? If you go back to that, it's the green bit. Okay? When it had switched at the input. So as the wave comes in, it starts over here, it builds up to V max or I max, right? And then it stays on my output. This is my output curve, is a full, okay, full wave rectification. All right. Now, essentially, that brings us to the end of that section on electrodynamics. All you've got to remember for the rectification is you start off, because your input is alternating current, right? So you start off with the plus and the minus and follow the plus through the circuit. So at your output, you found that it's a plus this way. Then switch it and follow the plus again with a different color pen or pencil. Follow the plus and find out where that is. That's going to tell you whether it's a half wave or a full wave, or I have seen a problem where in fact they had all of it in, but it ended up not being rectified at all. So the input wave and the output wave, actually, in fact, they were just transposed, but that's probably unnecessarily complex. So all in all here, you've got rectification, that's changing AC to DC, which is something that we can use, and then basically we can smooth it out at a later stage. All right, and that brings us to the end of this section. Thanks so much for watching it. Please remember, you have to get used to this, right? El pistolero or whatever. This guy also, you have to do that, change your book around, and realize that your alternating current is going to be coming in from your generator, and your motor is going to be taking that current. It needs a DC current, and you're going to be working out the thumb is the thrust on the motor, right? Just recapping those things. Please go back through it. These are short. They are intense. I know that. I know I've covered them quite intensely, but just follow what we've done here, and this section will be a breeze. Promise you. Cheers. Have a great time. Thanks for watching again. Bye.